So this is an interesting circuit that we're presented with, that we're asked to find the Thevenin equivalent circuit between A and B. So that's these two terminals here. And we notice in this circuit we have an independent current source of 8 amps. And then we also have this dependent current source, which is defined as 4 times I, where I is the current that's going to be flowing through this 4 ohm resistor. So let's see what's involved with determining the Thevenin circuit here. So the first thing we want to determine is the open circuit voltage between A and B. That will determine our voltage source in our Thevenin equivalent circuit. And the most reasonable way to do that is just take a path from A to B. And so we were going to choose, I'll highlight it. We'll choose this path here, where we go across the resistors, as it's much easier to determine the voltage drop across those resistors than it is any type of current source. So when we look at this, a couple of things jump out at us. The first thing we see is for this leg here, which I will now highlight in blue. When we look at this, we see we have this 8 amps coming up around here, and we see that there's no return path past this point. So none of the current goes this way because there's no path for it to come back. So that means that all of the 8 amps has to go down through the 4 ohm resistor. So that being the case, that tells us by observation then that I is equal to 8 amps. Okay, so the next thing we want to notice then is when we look at our dependent current source here. Now that we know what I is, we can determine what that is. And so that's easy enough. It's 4 times I, which we just said I is 8, so that's going to be 4 times 8, and that's going to be 32 amps. So then this equates to 32 amps with the circuit as it sits, the way we observe it. And again, we notice here that once the current comes out of here and comes to this node, there's no way for any of it to go this way because that's an open circuit, so it must all come this way. And so the same thing, we come to this node, none of it can go this way because there's no way for it to come back, so it must circulate around. So it's just a closed loop. So that being the case, if we pick another color here, let's say we'll go with the purple right here. So now we can say the voltage, we know the voltage across that resistor, right? So the voltage across the 12 ohm resistor then, using Ohm's law, which is just IR, we know that the current we just said is 32 amps, and the resistance is given on the circuit is 12. So that being the case, we can calculate that, and that comes out to 384 volts. So that's the voltage drop across the 12 ohm resistor. Likewise, we can go back to the blue, so the voltage across the 4 ohm resistor, again, using the same thing, just Ohm's law. We know that the current we said was 8 amps, and the resistance it says on the circuit is 4 ohms. So that comes to 32 volts. So now that's everything in our path, so we can come back and calculate our open circuit voltage. And when we do, it'll just be the voltage drop across the 12 ohm resistor plus the voltage drop across the 4 ohm resistor. And so that's going to be 384 plus 32. And so that comes out to 416 volts. So this is our open circuit voltage. So we'll use that in our Thevenin equivalent. So now we need to determine what the Thevenin resistance is. So let's reset our circuit here to make it a little easier to work with. So we undo all of this. So when we have a dependent current source, it's a little bit tricky. You can't really just look back into it like we traditionally do and just reduce the resistances. So what we're going to do, let me demark this. So we're starting afresh here. So now what we're going to do is we are going to short circuit this. So this is a short circuit, so we just put this wire in between. And when we do, we should have this current flow here, ISC. And so we're wanting to try to determine what that short circuit current is, because then we can use that to calculate the Thevenin resistance. So to do that, we're also going to arbitrarily label this node as V, and then we're going to write do some nodal analysis on this circuit. So let's do that. So the first thing we note then is we do have one independent source coming into the node. It's 8 amps. So let's start this. We're doing it for the V node. And so we'll set everything equal to that. So all the current leaving there is going to have to equal to this 8 amps coming in. So the first thing as we come across, or the next thing as we come across, we see this 4 ohm resistor. And so we can write the current from that branch. That's going to be, again, Ohm's law. And that's going to be voltage over resistance. So it's V over 4. So that should be the current flowing there. And then next, we will have this current source. And so this will be leaving our node, right? So, we can think about this as really all one big node here. And so that being the case, we can write that then as plus 4 times I, but we know that we just defined it as V over 4. So 4 times V over 4. And then finally, we will have the last thing here before we get to our short to ground. And again, we can just write that using Ohm's law as V over 12. So here's our nodal equation for that node V. And so now we should be able to take this and solve for the value of V. And this is, again, just an algebraic expression. So should be easy enough to solve. I'm not going to go through all that. This is for time's sake, but when we do, you should get V is equal to 6. So that's the voltage at the node. So now we should be able to use that to calculate I. And so remember, we have I defined as this current flowing through here. So to do that, then I through Ohm's law is equal to voltage over resistance. We now know the voltage is 6. We know the resistance is 4. And so that comes out to be 3/2 of an amp. 3/2 of an amp. So now we should be able to calculate our short circuit current, ISC. And so what that's going to be then is our current source. So that's going to be 4 times 3/2, right? And then that's going to be our voltage, our current flowing through the 12 ohm resistor. So that's going to be 6 volts over 12 ohms, the purple part that we have highlighted above. And so that's the two currents that'll be flowing into this node here, which will define our short circuit current. And so when we calculate that out, what this should equate to is 6.5 amps. 6.5 amps. So that's our short circuit current. And so now we can utilize this and the open circuit voltage now to find our Thevenin resistance. So RTH is equal to our open circuit voltage over our short circuit current. And so when we calculate that, that will be 416 over 6.5. And calculate that out, and that's going to be 64 ohms. 64 ohms. So now we should be able to derive our Thevenin equivalent. So we will have this voltage source here, which will be 416 volts. That's going to come up to this resistor here. And again, here's our A and our B. So we'll say A and B. And this is 64 ohms. So this is our Thevenin equivalent circuit for this circuit above.